Hey, we're here. I'm very happy to have Steve here with us today. And just a very brief introduction. Steve got his amazing degree here after doing something or other in Yale, dabbling in philosophy and other lovely things. And then after some detours, he ended up at Bard and is still at Bard. And I will let him speak.
Well, thank you so much. It's always a pleasure to be here and to be back at Courant and to the geometry seminar in particular. Thank you so much for having me. Okay, so I'm going to be talking about fan distributions, which are essentially going to be variants on more well-known mass or point equipartition problems. So yeah, I'll get started. Okay. So first thing, what are mass or point equipartition problems? So general situation is you're given a class of partition types of RD, usually into interior disjoint convex regions. I'll call them R1 through Rn. And then the question is, if you give me any M, say, finite measures on RD, say absolutely continuous with respect to the Lebesgue measure, can they be equipartitioned by one of these partition types? So by that, we mean that for each measure, it should be the case that the measure of the jth region is an equal fraction of the total measure. So in other words, the measure of RD over N. And this should hold for every region in your partition and every measure under consideration. So a discrete version of the question can be phrased as follows. Let's suppose I have any finite point set in RD, and I have an M coloring of X. So I have M disjoint subsets, and X is the union of those. All right. And now can I find one of these partition types so that the interior of each region contains at most 1 over N of each color class? Okay. So there's a very classical, very famous example of this called the ham sandwich theorem, dating back to 1942. And that says, so the discrete version anyway says that if you have a D coloring of any finite set in RD, then this coloring can be equipartitioned by the open half spaces determined by a single hyperplane each. So in each open half space, you have at most a half of each color class. So picture here is when D equals 2, and I have a collection of blue points, and I have a collection of red points. And then there is a line such that there's at most half of the red points on either side and at most half of the blue points on either side as well. And I should say there's many variants on equipartition problems besides these. The most famous one, arguably the most famous one, is seeking to extend the ham sandwich theorem instead of for one hyperplane in terms to many hyperplanes and so forth. And there's just a lot of research in this area. Okay, so the sort of motivating question for this talk is if instead of asking for a fair division of point sets in RD by full dimensional regions, what can we say about fair division of what will be necessarily small point sets in RD now by low dimensional sets? So in the ham sandwich theorem, the equipartitioning reasons for these half spaces, so codimension 0. And now we're asking, okay, what about equipartitions by, I don't know, certain linear flaps, by low dimensional flaps that are organized in some way. So the objects we're going to be looking at are what I'm going to call fans. So what's a fan? Well, first, we're going to say that a k-dimensional half flat B, what is that? That's the intersection of a k flat A with a half space. And that half space doesn't contain A. And then the boundary is a flat of 1 dimension or lower. And now a fan is going to be a union of these sorts of guys with a common center. So I'll say a k-dimensional fan is the union of R half flats, which we can think of as blades of the fan of dimension k, and they're centered about a common k minus 1 dimensional flat. So that's a picture of a 4 fan in R2, codimension 1. Okay, so given that, now we can talk about, instead of equipartition, equidistribution. So let's say I have a finite point set in RD, and again, I have an M coloring of that set. We're going to say that an R fan distributes X, and for this you don't even need a coloring, but it just distributes X if the fan contains all the points of X. So if it catches, the blades catch all the points of X. And then we'll say it equidistributes the coloring, equidistributes each of the Xi if the interior of each blade contains no more than an rth of each of the color classes. All right. So here's a sort of fanciful situation, which is very unlikely to happen in reality, which is, I can think of it as a projection of something that's going to happen in reality. But okay, let's suppose I have my 5 red points and my 4 blue points. Then this 4 fan here gives you an equidistribution of both colors. So there's at most a quarter of each type. So the interior contains it at most a quarter. So the center has to contain 1 point. So this situation would be very unlikely. This is a non-generic situation, but I wanted to give some sort of picture of what we're talking about, or the type of thing we hope can happen. Okay, so the results that we have are for 2 types of fans. The first is, I'm going to call it a conical fan, and that's given by a hyperplane arrangement. So let's suppose we have R hyperplanes in RD, R is at least 3. And let's suppose that any R minus 1 of the hyperplanes are independent, in the sense that their normal vectors are independent. But let's suppose that all R of them are not, so that they are dependent, and that actually also their intersection is non-empty, so that I have a R minus 1 dimension, codimensional flat, excuse me. So out of this, I can construct some blades. So for each, and some affine spaces. So for each J, what I'm going to do is I'm going to look at a half space coming from HJ, and I'm going to intersect that with all of the hyperplanes except the J minus first and the J. So each of these guys then is has codimension R minus 2. And I'm going to look at the union of these guys, and I'm going to have a R minus 2 codimensional fan, and the center of the fan is going to be the intersection of all the hyperplanes. So here's a picture. If we're looking at in RD and R is equal to 3, then we have our hyperplane, our line H1, another line H2, another line H3. And then our first blade over here is the intersection of this positive side of H1 together with H2. So that gives me the blue guy here. And likewise B2 and likewise B3. And that's how I'm getting my fan. Okay. So here is the results for equidistributions by conical R fans. So let's let D and M be. Oh, excuse me.
Going back, you do it cyclically? You said
I'm doing it cyclically. Yeah. Yeah.
Okay, sorry.
And then yeah, indices mod R.
I should be with you. Go on.
No, please. Right. Okay. So our results are going to hold for prime powers. We'll see why in a little bit. But let's let D and M be integers, and let's R be a prime power, at least as big as 3. And let's let N be sufficiently big. So R minus 1 times D plus M plus 1 plus 1. Then if you give me any M coloring of an affinely spanning point set of N points, and if I do this in Rn minus D minus 1, so D minus 1 dimensional lower than the number of points, then there's going to be a conical R fan which equidistributes each of the Xi. So I should say for a typical point set, if I look at the union of the interiors of the blades, that they have to contain at least a robust fraction of the number of points. You can't just stick everything in the center of the fan. So in fact, at least R minus 1 times D plus 1 points. And again, that number, you'll see where that comes from in a little bit. So here's an example, the lowest example of the theorem, and that's when R is equal to 3 and both D and M are 1. So then we're saying that if we have 7 points in R5, they can be equidistribution by a conical 3 fan. And if we're looking at a general point set, that at most 2 points lie on the center. So the picture here is of a projection. This is all occurring in R5, but I'm projecting into R2. In other words, I'm taking R5 and I'm modding out by the center. And then I have this equidistribution. So I have my 7 points, and then at most 2 lies on any open blade, and one of them is at the center of the fan. Or it could be that I have this picture, but there's 2 identified points, and 1 fewer on an open fan, on an open blade, excuse me. So that's for conical fans, and then we also considered fans that I'll call complex regular. So first of all, if I have a fan in RD, I'm going to call it regular if it's codimension 1, and the dihedral angles between the successive blades is always 2 pi over r. And for instance, so a regular 2 fan is in RDs is just an ordinary hyperplane then. And then I'll say that a fan in even dimensions is complex regular if it's regular and its center is a complex hyperplane. So that's sort of a special situation. So just as an easy picture, here is a regular 4 fan. So for complex regular fans, we have a very similar statement. So D and M are integers, and now we can let R be at least big. We can let R be equal to 2 now, and still a prime power, and let N be, again, sufficiently large. We've jumped up from D to 2D in the previous theorem. And again, if we have an uncoloring of a set now of complex affine spanning points, so they don't all lie on a complex hyperplane, then there's going to be a complex regular fan in Cn minus D minus 1, which equidistributes each of the colors. So as an example, and this is going to be, again, show that these sort of things hold for when the point sets are small. They have to be small. When R is equal to 2, let's say I have this set of complex affinely spanning points, 2D plus M plus 2 of them, and I divide X into M color classes in R to the 2D plus 2M plus 1 plus 2. Then the statement then is that there's a complex regular 2 fan, which is to say there's a hyperplane, and that hyperplane is going to contain X. And then inside that hyperplane, there's a complex hyperplane that's contained in H, and which bisects each of these color classes. So here's a picture of this. Again, this is the projected situation. I think this is with D and M are 2. So we're talking about 8 points in D plus M. So D and M are 2, then C5, so in R10. So you're talking 8 points in R10. All right. And the projection is that you have this line, and then here is the complex hyperplane. And you have equipartition in the usual language of the red set and the blue set, just like in that picture of the 2-dimensional ham sandwich theorem. Good. Okay. So just a little bit of word on optimality. It turns out we expect that these results are tight, but they're not quite, or at least I couldn't prove that they were quite tight. So to phrase this, let's let NRMD be the maximum integer, such that if you give me any M coloring of any affinely spanning point set, then points in RD, that we can find an equidistributing conical R fan. So then the theorem gives us a lower bound, and when D is big enough, this lower bound is almost tight. So, and I should also say this holds only when M is greater than or equal to 2. Once D is large enough, the results we have are essentially tight. So to phrase it, it's a little bit annoying, but let's let R be a prime power, at least as big as 3, and M greater than or equal to 2. And let's let D be an integer of the following form. So to the form R minus 2 times S plus T plus C, where C is a constant, and S is at least 1, and T is somewhere between 0 and R minus 3. So we can write any integer like this, provided it's big enough. And C is this constant here. So once you have D in that form, then the lower bound, the theorem gives the following lower bound, and then it's off by at most 2. So I guess asymptotically we're okay, but I would have liked there to be inequality there. All right. And likewise, in the complex setting, you can ask again for the maximum integer such that any uncoloring of a complex F-family spanning point set in CD can be equidistributed by a complex regular R-fan. And for here too, we expect things are tight, but we've only able to get an upper bound actually when R is equal to 2. So at least in those pictures that I had before. So now when M is at least 1 and you express D in this way, then the lower bound that you get from the theorem is this, and then you have the following upper bound. So again, off by 2 once D is large enough. Okay, so now I want to talk about a type of generalization of the theorem, this equidistribution theorem. I'm going to call it piercing distribution. And this is based on a generalization of the ham sandwich theorem that goes back to Dolnikov in 1992. So the statement is this. Let's suppose I have F1 through FD, and each of these guys are finite families of compact complex sets in RD. And each of the families is intersecting. So by that I mean, if you look at any one of these families, if you take any 2 members in the family, they intersect non-trivially. Then the claim is if you have that, then there exists a hyperplane which pierces all of these guys. So in other words, it's a hyperplane transversal. It intersects every member of each of the families. So a discrete version of this statement, which actually with some work, it's actually equivalent, but we don't need that for this. We can say this. So let's let X be a finite set in RD, and let's suppose I have D intersecting families of just subsets of X. Then you can find a hyperplane which intersects the convex hull of every member of the family. So this follows quite quickly just by looking at convex hulls. All right, so another way to say this, and this will be helpful in a second, is that instead of saying that there's the hyperplane that intersects the convex hull of every member, another way to say that is that if you look at every member A, then it can't be contained in either of the open half spaces determined by the hyperplane. It can't completely lie to one side or the other. Right. So I said already that this is a special, the ham sandwich theorem is a special case of this theorem, but you can think of it as sort of the balanced case of a more sort of unbalanced distribution or piercing result. So here is how the ham sandwich theorem follows. And this is in the paper, the Dolnikov paper. So let's say I have my finite set and give me a D coloring of it. Then for each color, I'm going to look at a corresponding family of sets. Namely, I'm going to look at all the subsets of X that contain more than a half of the points of Xi. Then each one of these families has to be intersecting just by the pigeonhole principle. So you have a hyperplane that's guaranteed by Dolnikov's theorem. And the claim is that this hyperplane actually bisects each of the Xi. And the reason for that is if it didn't, then there's going to be some half space and some color class such that Xi is lying, so the parts of Xi that lies in the open half space has more than half the points of Xi. Okay, but that means by definition that the intersection of that open half space and X, or everything that's in X that's in the open half space, will actually be a member of Fi. Oh, it says member of A here, excuse me. It should say is a member of Fi. But if it's a member of Fi, well then it shouldn't be lying in either open half space. So then that means that H plus intersecting with H isn't a subset of H plus, and that's absurd. Yeah, sorry about that. This should be an FI here. Is it okay? All right. So our generalization of the equidistribution results, I'm going to call them piercing distributions. These arise by replacing this non-disjointness criteria on the families with a weaker R-fold version. So we have a theorem, again, both for the conical fans and for complex regular, and it goes like this. So let's suppose that D and M are integers and R is a prime power. So for the conical, again, let's suppose that R is at least 3. And let's suppose I have a set X of at least these many points, the same as in the equidistribution theorem, affinely spanning. And now let's suppose I have M families of non-empty subsets of X, and they're not intersecting, but it's a weaker criterion that if I look at each one of these FIs, none of them contains R pairwise disjoint sets. So if R equals 2, that would be the same thing as intersecting. Then under this assumption, you're going to get a transversal result. So now there's going to be a conical R fan that it's not the case that it intersects the convex hull of these guys, like in Dolnikov's theorem, but actually that for each member of the family, it's going to have to be intersected by at least 2 closed blades of the fan. And likewise, you have the same thing in the complex setting, same number of points, same condition, no R pairwise disjoint subsets. So instead of saying that every member of each family is intersected by 2 closed half-lats of the fan, you could just say, probably a little more succinctly, that no member of any family is contained in the interior of any blade. Maybe that's easier. I think so, but it can't be completely contained inside of any open blade. So just like before, just like Dolnikov recovers the ham sandwich theorem, this theorem recovers the equidistribution results. So let's look again at M coloring now, and in R n minus d minus 1 or C n minus d minus 1, doesn't matter. And again, for each color class, we look at the corresponding family, subsets of X, such that they contain more than an R of the points of the color class. And then we have a guaranteed R fan from before, and we have that no element of any of the families is contained in the interior of any of the blades. Then again, this R fan is going to have to equidistribute, because again, if it didn't, then that means that for some J and some I, the interior of the blade contains strictly more than an R of the color class. And so then it would be an element of this family. But if it's an element of the family, then it can't be contained in the interior of any blade. And okay, then that's your contradiction again. So when R equals 2, you get a sort of complex version of Dolnikov's theorem. So now we can say this. Again, let's look at this many points, 2D plus M plus 2. And let's suppose I have M intersecting families, because now R is equal to 2, so that means I'm actually intersecting. Subsets of some set X, that's affinely spanning. Then now you're saying there's a regular 2 fans, so again, a hyperplane, a real hyperplane, lying in CDM plus 1. And this real hyperplane contains all the points of X. And there's a complex hyperplane inside that hyperplane. And that complex hyperplane actually has to intersect the convex hull of every member of your family. So in Dolnikov, you have a hyperplane that's transversal to everything in the set. And now we have this complex hyperplane that's transversal to every member, to the convex hull of every member. because they can't lie in the interior of any of the two flats. Okay, so we'll see how much time I left for proving things. All right, so the proof of this transversal result, and I should say there's other distribution results in the paper, but almost certainly won't get to them here, but you can have distribution results from multiple fans as well, just focusing on the single fan case. So, and the ingredient for all these proofs is the same. We're going to derive these fan distributions, whatever they are, from Tverberg-type theorems. And not just from that, we're going to use Gale duality very, very heavily to do so. That's going to allow us to translate between Tverberg theorems and fan distributions. Right. So should probably mention Tverberg theory a little bit anyway. So Tverberg's theorem, 1966, is this cornerstone result in discrete geometry and convex geometry that says if I have a set consisting of at least r minus 1 times d plus 1 points in Rd, then I can find r pairwise disjoint subsets such that even though the sets themselves are disjoints, their convex hulls all overlap. So here's a picture when r is equal to 4 and d is equal to 2. Tverberg's theorem is saying that we have 10 points in the plane. And the claim is you can divide those 10 points into 4 sets. The 4 sets are disjoint, but the convex hulls all overlap. And that is what's going on here. This set, and the convex hulls of these 2 triangles. I should also say that the case when r equals 2 is Radon's theorem. If you look at any set of d plus 2 points in Rd, you can divide them into 2 disjoint sets with overlapping convex hulls. Right. So there's many, many generalizations of Tverberg's theorem. I don't know, I've never checked the number of papers that deal with Tverberg partitions and variance versus the number of papers that deal with mass partitions, but I bet you it's about the same. So one way to generalize Tverberg's theorem is topologically. And this starts out by reframing Tverberg's theorem in terms of affine linear maps from an n-1 dimensional simplex to Rd. Namely, if I have n points in Rd, I view them as coming from the vertices of a n-1 dimensional simplex. And then what I do is I consider an affine linear map there. So in other words, just I affinely extend that map. So that way, convex sums of the vertices get sent to convex sums of the images. And if you take that view, then a Tverberg partition of your collection of points, so you're partitioned into these R points where the convex hulls all interlap, that's the same thing as saying, if you look at the level of the simplex, that there's R pairwise disjoint faces of the simplex whose images all overlap. So I'll have a picture in a second. And with that view, you can ask well, can you extend Tverberg's theorem from affine linear maps to just arbitrary continuous maps? And the answer is generally no, but it is true when R is a prime power. And that's been known since 1987. And counterexamples to this were given in 2015. It's a nice history of things. I don't want to really get into it right now. But the statement is this: if R is a prime power and n is at least r minus 1 times d plus 1 plus 1, then if you give me any continuous map from an n-1 dimensional simplex to Rd, then it admits what I'm going to call an R-Tverberg tuple. So that means these R pairwise disjoint faces such that the images all overlap. So here's a little picture when R is equal to 2 of topological versus, or non-topological versus topological Radon's theorem. So you have your 4 points in the plane and you're viewing them as coming from the 4 points on this tetrahedron. This would be an affine map. And then this is a more general continuous map. And no matter what, you have opposite edges on this tetrahedra that get mapped. Their images overlap. Okay. So for our purposes, what I am going to need is an extension of Tverberg's theorem due to Sarkaria that's been known since 1990. And this is saying, essentially, if you give me more points, then you can get Tverberg tuples that satisfy additional properties that you may want. So, and in fact, this theorem can be proven directly from the topological Tverberg theorem via what's called the constraint method, for people who have heard of that. That was important in disproof of the topological Tverberg conjecture. Okay, but that's probably getting too far afield. So now let's let m be an integer, greater than 1, r prime power, and now instead of r minus 1 times d plus 1 points, we look at r minus 1 times d plus m plus 1 points. And now suppose that we're given, so somewhat very similar to this statement of our like Dolnikov generalization. Now let's suppose I have m non-empty families of subsets of n, which I'm going to view as the vertices of my n minus 1 simplex. And let's suppose that if we look at any of these families, if I look at an Fi, then it does not contain R pairwise disjoint sets, just as before. Then you can be ensured a Tverberg tuple in this situation, such that if I look at any member of any family, it's not going to be completely contained in the vertex set of any of my sigma j's coming from the Tverberg partition. Right. So ultimately, the transversal result is going to follow from that theorem. And you can do similar things with other Tverberg type theorems. All right. So the main idea is that we're going to apply Gale duality to the linear versions of these topological Tverberg type theorems. So in other words, looking at the affine linear cases. So I should say, just not to be remiss, that this work is continuation of previous works where Gale duality was applied to radon type theorems. And doing that, we were able to generalize the Dolnikov transversal results to multiple hyperplanes. All right. So I won't go into, can't go into too many details of construction, but I'll just sort of describe a little bit what I can. So what does the Gale transform do? Well, it gives us a correspondence between sequences of endpoints in KD, so K is either R or C, which affinely span KD, and sequences of endpoints in K n minus D minus 1, which linearly span and are such that the barycenter is the origin. So the crucial property that we use is that affine dependencies amongst the AI correspond to what I'm going to call dispersals of their Gale transforms about linear hyperplanes. So to put this a little bit more precisely, say that I have a non-zero n tuple of lambdas, and I have my affine dependency here. Then the claim is that there's a non-zero vector in Kn minus D minus 1, such that the inner product of alpha with the Gale dual Bi is precisely equal to this coefficient lambda I. So what that means in particular is that if we look at any of the lambda i's that are 0, so those are coming from what I'm going to call unused AI, they wind up on this linear K hyperplane. And then how the BIs are dispersed about that linear hyperplane is given by this. It's just completely given by the coefficients. And the converse is true too. If you start off with a non-zero vector and you look at the inner product, then you're going to get an affine dependence amongst the AI. So here's a little picture. I have 4 affinely dependent points. And I could say, I don't know, this one is like a quarter, and minus a quarter, and minus a quarter, something like this. And then I have a linear hyperplane, namely the origin here, that separates the positive and the negative. So the main thing we do is just that using that property, we have that these proper, what I'm going to call proper Tverberg partitions, correspond precisely with distributions by linear conical fans. So the conical fans were determined by hyperplanes. And in this situation, these the hyperplanes are going to all be linear hyperplanes. And something similar will happen with linear complex hyperplanes. So ones where the hyperplane is a linear complex, is a linear space. Okay, so what do we mean by proper? Well, we have a Tverberg tuple. It's proper if when we look at this equality, we have number one that if you look at I sub 1, that all the TIs are positive. Likewise, I sub 2, all the TIs are positive, and so forth. And they sum to 1. It's going to be convex. And secondly, that TI is going to be 0 for all the AIs that are not involved in the Tverberg partition. So given that, we can look at an analogous idea for fan distributions, namely if I have endpoints in RD, and I look at R non-empty pairwise disjoint subsets, then I have that my fan distributes these guys. I'll say distributes the xi according to the ij, if, okay, it contains all the points. And if you look at the interior of any bj, it contains xi for all I in ij. And then everything else that's uninvolved is in the center of the fan. So this is probably a mouthful, but I'll just say, I should also check on time. I say that there's a one-to-one correspondence between these two ideas. So namely, if I have a proper Tverberg tuple for a linear map corresponding to AI, when I look at the Gale dual, there's a linear conical fan distributing them, and it distributes the BI according to the IJ in this exact same distribution pattern. And the converse is true as well. If I have a bunch of pairwise disjoint sets, and that I have a linear conical fan which distributes those according to the IJ, then there's going to be a proper Tverberg tuple for the AI such that the vertices of my sigma j are precisely the IJ. And likewise, same statement in the complex case, except we only have one direction. Namely that if you have a proper Tverberg tuple, then you're going to be able to get a linear complex regular fan that distributes them according to the IJ. We don't have the reverse. I think we should, but we don't have the reverse when R is at least 3. However, when R is equal to 2, we do have it. And it's this sort of bridge that's created here that allowed for us to get upper bounds on our results, the upper bounds that we're talking about a little while ago. Namely because Sarkaria's result is optimal. So by being able to go back and forth along the bridge, essentially the equidistribution results are optimal too. But there was a little bit of, I don't want to go too much into the weeds, but I had to force things to be linear to do that. And that's why we got those 2 extra points instead of being height. Okay. So with this, I think we can give a sketch of the fan transversal theorem. So you give me your finite point set of n affinely spanning point sets in kn minus d minus 1 of the correct size, whether k is equal to r or k is equal to c. And now take that and lift it into kn minus d, lift it all to be height 1. And if I look at b1 through bn, okay, those are the lifted points. And those points, by assumption, since they're the xi affinely span, the b1 through bn linearly span. But they're not going to sum to 0. So you throw in this dummy point, b sub n plus 1, so that now you can say that b1 up to bn plus 1, these are the Gale transform of some points a1 through an plus 1. So I've inserted an extra point, but we'll see this won't wind up mattering. Okay. So now I'm going to consider the linear map from an n plus 1 dimension, from an n-dimensional simplex, so on these n plus 1 points to kd, be the linear map that says take I and spit out a sub I. And for this, I'm viewing CD as R to the 2D. So by assumption, we're starting off that we have these non-empty families of subsets of X. And if I look at any one of these families, you don't have R pairwise disjoint members. That just does not happen. Corresponding to each one of these families, I'm going to define a new family, F sub I prime, to be subsets of N. And it consists of all those I1 through IK such that X sub I1 through X sub IK are in F sub I. So there's a, okay. clear correspondence between these guys. And since each of these f sub I doesn't have R pairwise disjoint sets, then each f sub I prime doesn't have R pairwise disjoint sets either. And that means now we're in a position where we can apply Sarkaria's theorem. So actually where we're going to apply it, remember we have this sort of extra point, 1 through n plus 1. We're just going to apply it on the first n guys, a1 through an. And we can do this because the numbers are correct. So this gives us a proper Tverberg tuple for the restriction, and therefore also for the full thing. So that if I look at the vertex set of each of these sigma j, each of them is contained in n, and none of them contain any element of f prime, of the union of the f sub I primes. Okay. So in particular, a sub n plus 1 is uninvolved in this Tverberg partition because it's not involved here. So now I apply this linear fan lemma. So the linear fan lemma says, okay, there's a linear R fan in Kn minus D, such that when I look at the Gale duals, all the BI are in the interior of the blades for each I and ij. And all the BIs are in the center for all the AI that were uninvolved. In particular, a sub n plus 1 was not involved, so b sub n plus 1 lies in the center of the fan. I remember we're in a dimension higher sort of than we should be. And the last coordinates of this actually is negative n. So it's not going to be in that plane that we lifted to. All right. So I'm not going to go to details of this, but what we do is for each j, look at the intersection of the hyperplane hj, look at the intersection of hj with the height 1 plane. So this gives me an hyperplane inside of this space, Rn minus d minus 1 / 1. So I'm looking at that, and then I'm going to project it back down to where I should be, which is in Rn minus d minus 1. All right. And I do likewise the same thing for the blades. And then I get what is going to be a conical R fan in Rn minus d minus 1. And I should say that if we look at B1 through Bn, those are all in the fan, and they're all at height 1. So x1 through xn are going to be down below, are going to be on my fan. And on the other hand, the dummy point is not. And likewise, we do the same thing when we're looking in the complex case. We look at the intersection of the linear complex hyperplane with the height 1 space, the n minus d minus 1, and likewise for the fans, for the blades. Project down, and again, we have a regular R fan centered about a complex hyperplane. So by construction, we have that our R fan, which is in Kn minus d minus 1, it contains every point of x, because the other one contained everything at height 1. So it's distributing. And now we have to show that if I look at any A from any of these families that we started off with, that it's not completely contained in any open blade. So to that end, let's let I be in M, and let's take A from one of these families. And let's let A prime be the corresponding element of Fi prime. Then under the sort of, I guess, the duality, the Gale duality, we have that A is completely contained inside the interior of Bj, and Bj is coming from the 1 in Kn minus d, if and only if A prime is completely contained in Ij, the vertices of sigma j. But when we're looking at all our guys X, they're contained in these blades, the B sub j double primes. So what we have then, this winds up being the same statement as just saying the following. A prime is not contained in any of the IJs. So A isn't contained in any of these interiors, but everything is in A was at height 1. So A is not contained in the interiors of any of the R fans that are in the appropriate dimensional space. And that completes the proof. So how am I on time? Doesn't make sense. So that's usually like 5 minutes for question, 10 minutes for questions.
You're asking for questions because you're done, or because
No, I'm saying I can go and just like sort of slam through like some more slides for 5 minutes, or okay. All right. Okay. So I'll just briefly mention then that we have extensions in the paper of Sarkaria's theorem for multiple Tverberg pairs instead of just for one. And this is going to allow us to extend the results that we have these transversal fan results for multiple R fans. So this is a bit of a mouthful to state. So we have dm r and n are integers at least one. R greater than 3 is prime, no longer a prime power, just prime. And let's suppose when I look at the R area coefficients of m times r minus 1 over 2, that they're all even. So in that expansion, they're all even. And then I'm going to let n be at least as big as, instead of r minus 1 times d plus 1 plus m plus 1, I'm going to have here m times r squared minus 1 over 2. Essentially, this is just so the number of conditions matches the target space when we go sort of into the equivariant topology of the situation. Okay. So now let's suppose that I have a continuous map, and then I have families of non-empty subsets of n, such that instead of no R pairwise disjoint sets, I have no R squared pairwise disjoint sets. Then I can find two Tverberg tuples, sigma 1 through sigma r, and tau 1 through tau r, so that if I look at any member of the union of these families, it's not going to be a subset of the intersection of the sigma j and the tau k's. So if you look at any of these R squared sets of this form, intersects sigma j with tau k, and look at the vertex set, it's not going to contain any member of any family. So Sarkaria is for R, and it's one guy that satisfies this. So in essence, this can be seen as guaranteeing two maximally distinct tuples. The sigma and the tau j's are going to be as distinct as can be made. Right. And just a technical point, this condition on even coefficients, you can, as a special case, you can always let m be r to the l minus 1 divided by r minus 1 and then times 2. So there's an infinite family of n for which this works. In fact, there's more, but that's fine. And this is a standard Bohr-Coulomb type theorem. You make a configuration space for this and a test map, and the theorem reduces to showing that if you have a continuous map that's equivariant from one space to another of the same dimension, that it's going to have a zero. And that's how you can prove a topological Tverberg, all sorts of things. So that's pretty standard. All right, and it also gives transversal extensions of the equidistribution results we had for a single R fan for multiple R fans. So just as before, let's say I have an M coloring of finite set X, and I have two fans now, two R fans. Then they equidistribute the Xi if each of them distributes. So in other words, if the point set lies in their intersection. And moreover, when I look at the interior of one blade and the interior of the other blade, I intersect those, then I'm not going to have too many, I'm not going to have more points of Xi than I should. So the number of points in Xi that are inside the intersection is no more than R, 1 over R squared of all the colors, of all the points in that color class. So then under the exact same sort of assumptions of the Sarkaria situation, we can say, yeah, if n is sufficiently large, namely this large, and we have an M coloring of a affinely spanning point set, then it can be equidistributed by two conical R fans. And likewise in the complex setting, we have the same thing. Yeah, so probably most important slide. Thank you.